In the previous lesson, we saw that a balanced three-phase set is three equal vectors, spaced 120 degrees apart, summing to zero. That picture lives on a phasor diagram. Now we connect it to a real circuit. The most common topology is Y to Y, a Y source feeding a Y load. Once we draw it, two new questions appear naturally. What is the voltage between two lines, and how does it relate to the voltage you measure to neutral? Here is the standard YY connection. On the left, three sources, VA, VB, VC, share a common point N, the source neutral. On the right, three load impedances ZY share their own common point N, the load neutral. Three conductors called lines A, B, and C carry power from source to load. A fourth wire connects the two neutrals, that is, the neutral line. The voltage measured from one line to neutral is called a phase voltage. The voltage measured between two lines is called a line voltage. In a positive sequence balance set, the three-phase voltages are written. VA equals VP at angle 0 degrees, VB equals VP at angle minus 120 degrees, and VC equals VP at plus 120 degrees. Same magnitude VP, same frequency, spacing fixed at 120 degrees. This is exactly the symmetric set from the previous video, now anchored to specific terminals on a real circuit. The line voltage VAB is the voltage at terminal A measured with respect to terminal B. By Kirchhoff's voltage law, VAB equals the phase voltage VA minus the phase voltage VB. So if we know the phase voltages, the line voltages drop out by simple subtraction. The question is, what does that subtraction look like geometrically? Watch the construction on the phasor plane. Start with VA along the reference axis. VB sits at minus 120 degrees, pointing down and to the right. To form VAB equals VA minus VB, we flip VB to get its negative. That swings it up to plus 60 degrees, and add it tip to tail to VA. The two vectors form a rhombus, and the diagonal from the origin to the far corner is exactly VAB. Two equal sides of length VP meet at an internal angle of 60 degrees, so the diagonal length comes from the cosine rule, square root of 3 times VP. The diagonal lands at plus 30 degrees. VAB leads VA by 30 degrees, with magnitude root 3 VP. Here is the result you carry forward. The line voltage magnitude is a square root of 3 times the phase voltage magnitude, about 1.732 times larger. The line voltage leads the corresponding phase voltage by 30 degrees. The other two line voltages, VBC and VCA, follow the same pattern. Same magnitude root 3 VP, each one rotated by another 120 degrees. Three line voltages form a second balanced star, larger and rotated 30 degrees from the phase star. Now look at current. In the Y connection, each phase impedance sits between one line terminal and the neutral. There is no branching. The current leaving terminal A goes straight through impedance ZY. That single conductor carries everything. So in a Y load, the line current equals the phase current. No square root of 3 here. This identity is purely geometric, free from any extra calculation. Each phase delivers an average power equal to V phase times I phase times cosine theta, where theta is the angle between phase voltage and phase current, the impedance angle. With three balanced phases, the total average power is 3 V phase I phase cosine theta. We can rewrite this in line quantities. V phase equals V line over root 3. I phase equals I line. Substituting and simplifying, the total power becomes root 3 times v line times I line times cosine theta. Same number written two ways. The reactive and apparent powers follow the identical structure. Let us put numbers on it. Take a balanced Y source with phase voltage 120 volts RMS, positive sequence. Each leg of the Y load is ZY equals 10 plus J 5 ohms. First, the magnitude and angle of ZY. The magnitude is square root of 125, which is 11.18 ohms. The angle is the arctangent of 5 over 10, which is 26.57 degrees. Phase current. I phase equals V phase over ZY, which is 120 divided by 11.18, giving 10.73 amperes RMS, lagging by 26.57 degrees. Line current equals phase current, 10.73 amperes. Line voltage equals root 3 times 120, which is 207.85 volts. Cosine of 26.57 degrees is 0.894. Total power. Root 3 times 207.85 times 10.73 times 0.894 equals about 3,454 watts or 3.45 kilowatts. One more important consequence. In the balanced case, the three line currents IA, IB, IC form a balanced set themselves, each rotated by 120 degrees. Their vector sum is zero, exactly like the voltages, so the current returning through the neutral wire is zero. An ideal balanced YY system needs no neutral conductor at all. The neutral simply rides along, carrying no current. Two key takeaways. In YY, line voltage is root 3 times phase voltage and leads by 30 degrees, while line current equals phase current. Total power is root 3 V line I line cosine theta or 3V phase I phase cosine theta, the same number in two languages. Next, we look at delta connections, where the same square root of 3 factor reappears, but this time on the current side.